Diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotonic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
What happens to a cell when it's placed in a hypotonic solution versus a hypertonic solution? A hypertonic solution is simply a solution that has a lower concentration of solutes, dissolved substances, compared to the inside environment of a cell. For example, water is considered a hypotonic solution since it is very low in solutes. A hypertonic solution is a solution that has a higher concentration of solutes compared to the cell's inside environment. For example, water with a lot of salt is considered a hypertonic solution since it is very high in solutes. How can we examine the effects of a hypertonic solution on a cell? You might be thinking, well, I'm made out of 50 to 70 trillion cells. If I drink this, I'll know what happens to cells in a hypertonic solution. But do not do that! Drinking salt water can be very dangerous as it severely dehydrates you. Nausea, vomiting, and even hallucinations are just a few symptoms of drinking massive amounts of salt water. Ask anyone who's been stranded at sea, which is unlikely because people who drink seawater eventually died due to kidney failure. So what you really need is a lab animal to conduct your test. Darn, she's too smart. Time to try her older brother. Well, that was a bad experiment. What's a better way to test how a cell reacts when placed in a hypertonic solution? Some eggs, like chicken eggs, are surrounded by a hard outer membrane which protects the semi-permeable inner membrane. This membrane is semi-permeable because it allows substances to leave and some substances to enter. In particular, the semi-permeable membrane allows water to both enter and leave the cell, but large molecules, like salt or sugar, are too big to pass through. The question is, how can we examine the semi-permeable qualities of this inner membrane with the hard eggshell in the way? Dissolve the outer shell by placing an egg in vinegar. Vinegar has a chemical called acetic acid. Eggshells contain calcium carbonate. When calcium carbonate in the eggshell comes in contact with acetic acid, a chemical reaction occurs. Calcium carbonate will break down to form carbon dioxide, water, and calcium acetate, thus dissolving the calcium carbonate shell. Within seconds, you'll see bubbles form. These bubbles are carbon dioxide that are produced when acetic acid breaks down the eggshell. Within 3 days, you should have a semi-permeable membrane free of the hard outer shell to conduct your experiment. Before starting our experiment, we will first mass our egg using a scale. Egg A has a mass of 94 grams. Egg B has a mass of 103 grams. Egg A we will place in a hypotonic solution, water. Egg B will place in a hypertonic solution, thick and sugary corn syrup. Egg A now has a mass of 97 grams. Egg A increased slightly to 103% of its original weight. We can conclude when a semi-permeable cell is in a hypotonic solution, water will enter the cell. Egg B now has a mass of 59 grams. Egg B decreased to 57% of its original weight. We can definitely conclude that when a cell is in a hypertonic solution, water will leave the cell. In fact, this is evident by the layer of water sitting on top of the corn syrup. However, 103% change in mass is not very significant. So how about we try this experiment again, but switch the eggs? This time, egg A is going in the hypertonic solution, which is still on the right. Egg B is going in the hypotonic solution, which is still on the left. After several hours, mash your eggs again. Egg A went from 97 grams to 55 grams. Egg A has decreased to 57% of its original weight. Egg B went from 59 grams to a whopping 105 grams. Egg B has increased in weight to 177%. From this experiment, we can definitely conclude that when a cell is in a hypotonic solution, like water, water enters the cell. On the other hand, when a cell is in a hypertonic solution, like corn syrup, or more realistically salt water, water will leave the cell. Now that you're done with this experiment, time to play with those shellless eggs.
No! You're just gonna